Hello and good afternoon, everyone. Today, inshallah, we will continue this session. We will go through the composite functions. We will continue our journey, the homogeneity and the mean value theory. This is very, very important. I want you to go through it. Of course, as you know, all the course resources, you will find them on Moodle, and I would advise deeply that you visit Moodle frequently, because you will have plenty of exercises over there, plus the previous exams, which is going to help you out a lot. And also will help you to understand the nature of the exams and how it is formed. It's very, very important to visit it as much as possible. Also, as you know, the recorded lectures, you will find them all on the YouTube channel. So you will be able to catch up just in case. All I want you to do is to try as much as possible to resolve these problems once more using your hand. This is very, very important in order to gain time and in order to collect the information and to have them all in your mind. Because some of these exercises will be confusing unless you write it and use your pen in solving these problems. Today I will talk with you, or in this session I will talk with you with the higher order derivatives and to see how to get it in the case of composite functions. I want to review what we did in the previous section. So in the previous session, we had, for example, like z as a function in u and v, where function f is given by u squared plus 3v, where you have u by itself is given by x squared y, and the v by itself is given by xy plus e to the power of 1. And it is required in this problem to find the first partial derivative of z with respect to y. As we learned in the previous session, all I have to do in order to get a solution of this problem, it's really very simple. I will have first to identify the functions involved in this example. So if you remark, you will have z as a function in both u and v, and in these variables. And each one of these variables is by itself another function in x and y. So all I have to do in order to get partial z, partial y, or partial z, partial x, I can do the following. First, I will try to differentiate. I will write partial z, partial y, which is equal to, I will differentiate the function z with respect to its own variables. The variables that exist in z are u and v. So simply, it's going to be partial z, partial u, plus partial z, partial v. Then I will use the chain theory, like what we did in the previous session, to move to the second step, which assigning this derivative for the variable x, which is one of the variables that already exist in u. So all I have to do is to multiply by partial u, partial x, times partial v, partial x. This is if I'm getting the derivative with respect to x. As I'm getting the derivative with respect to y, regard the similarity that I will differentiate the z function for its variables. So partial m, partial u, partial m, partial v, but I will multiply by partial u, partial y this time, times partial v, partial y. So it's really very simple, straightforward. I will differentiate first z with respect to its own variables, then each one of them will be differentiated to the required variable. It will depend with it. So if I want to do so for, let's do the derivative with respect to x, since the derivative with respect to y already exists on the slide. So I will do this with x for u. So the first step is to differentiate with respect to u. So I'm going to differentiate z with respect to u, which is going to be a 2 over u, as you can see, plus differentiating z with respect to v, which is going to be simply 3. Then I will multiply by the derivative of u with respect to x, which is simply 2 over x, and I will multiply by the derivative of v with respect to x, which is going to be Of course, differentiating with respect to x, x times y, it will develop just only y. And differentiating with respect to x, e to the power of y is going to be 0, partial. So the second step is to substitute and finalize. So it's going to be equal to 2. I will replace u by its value, which is x squared plus y. All of this will be multiplied by 2x plus a 3 over y. Then I can simplify it or expand it or taking common factors, whatever. If it is a multiple choice, then I will choose the correct answer. It's really very simple. Okay, if I want to get the derivative with respect to y, it's going to be exactly the same. So if I want to get the derivative with respect to y, I will get these two guys which already exist with me. Very similar. The change will be in the values of u. So once more, differentiating with respect to u, it will develop 2 over u. Differentiating with respect to v, it's going to develop just to only 3. The next step is to get the derivative partial u, partial y from this guy, which is going to be 1, and then differentiating v with respect to y, which will develop x times e to the power of y, as you can see, x plus e to the power of y. Then I will get them all together by the substitution of this root. All I have to do is to start substituting. So I will replace partial f, partial u by 2u, then times partial u, partial y by 1, then plus partial v, partial partial f, partial v, which is going to be 3 times partial v, partial y, as you can see. And also in a similar manner, I will replace u by x squared y and then simplify, as you can see. It's really very simple, straightforward. There is no problems whatsoever. Okay, if I try to solve this problem, here he is asking us to find the derivative of this function, which is as given. W is a function in x, y, and z. It is x squared times f, where f is z over x and y over x, or a function in z over x and y over x. So, and he requires that we find partial w partial x. I would recommend to start by considering w is equal to x cubed times f, and the f is a function of u and v as we did previously. I will consider u to be z over x and consider v to be y over x, for example. And then I need to get partial w, partial x, which is going to equal to, I will do 2 steps. The first step is to differentiate the function given with respect to x, and once we do so, we will remark that we have 2 functions multiplied in each other. X cubed times f, which is an arbitrary function, of a u and v. So now I know that w is simply x cubed times f of u and v. So once you stop the differentiating, you will have the multiplication rule of 2 functions, which can be put simply as 3 over x squared times f over u and v, then plus x cubed times f of u and v, and then I will do the partial derivative for this guy by itself with respect to x. So let's get to that guy by himself. So now I want to differentiate partial f, partial x. Differentiating partial f, partial x by itself, it's a composite function in u and v, and each one of these functions is a function in x and y and z, as you saw. So first, I will differentiate partial f, partial u, then plus partial f, partial v, then times partial u, partial x, times partial v, partial x. I will exactly do that. So it's going to equal to partial f, partial u. It will remain because I have an arbitrary function. A general function. It's not actually it's not identified with respect to it. Okay, but I have partial u, partial x. And the partial u, partial x, I'm going to differentiate this guy, which is z times x to the power of minus 1. So partial u, partial x will equal to minus z times x to the power of negative 2. And also I will need the derivative of v, and the v can be put simply as y times x to the power of negative 1. So simply partial v, partial x is going to be minus y times x to the power of negative 2. This is what I'm going to use. Now I will have to put everything together. So it's a partial f, partial u times partial u, partial x, which means minus of a z times x to the power of negative 1, then plus partial f, partial v, and in a similar manner times partial v, partial x, which is y times x to the power of negative 2, and there is a minus sign in it. All of these values, don't forget that all of this is just only a part of the main problem, it should be here. And this will lead us to the following. Partial w, partial x will equal to a 3 over x squared times the general function of the general function of f, u, and v, then plus x cubed, open bracket, and then you will have u derivative, which is simply partial f, partial u, times negative z of an x to the power of negative 2 plus partial f, partial v times minus y times x to the power of negative 2. Then I will simplify by multiplying x cubed one time in negative z x to the power of negative 2, and then x cubed times this guy, as you will see. So all I have to do right now is just easily, first of all, differentiating, then trying to separate everything nicely. So once more, okay, here we go. Exactly in similar manner, I will call it j du by dx times v plus u dv times over dx. That's the law of the multiplication of two functions. So once you try to use this relation, all I have to do is to differentiate first x cubed to be 3x squared times f. Then I will have x cubed times the derivative of the function f, which I can consider a function in u or v, or a or b, as I did here, considering z over x by a and y over x by b. Now I'm getting f of a and b in a similar manner. Okay, of the same steps, I will do exactly the same, considering this function. So I will differentiate first with respect to a or with respect to u, as you can see, times partial a, partial x, and then differentiating f with respect to b, times partial b, partial x, as you can see. Okay, for the derivative of b with respect to x, I already have it. For the derivative of a with respect to x, it's very, very simple from those guys, which is z over x and y over x. And then I will start multiplying exactly as we said, and as we did, I'm sorry, in the previous example. Then I will take this value, substitute it here, and multiply it by x cubed, and that's the final result. This is how to get partial z, partial x. If I want to get the second derivative, now I have the first derivative. If I want to get the second derivative, it's going to be exactly the same. The second derivative is really very simple. This is the function that I have. I have to get the first derivative first, then I will go for the second derivative. Now I will do the second derivative, but with respect to y. So now I have the first derivative with respect to x, and which is given, as you can see, by 3x squared of a function a and b, minus x z partial f partial a, which is also a function in a and b, minus x times y, partial f partial b, which is a function in a and b. Now I need to differentiate all of this once more, but in this time with respect to y. How to do it? I will take each part of these first derivative, and then I will differentiate, but with respect to the other variable. So I will start with this guy. If you remark, I will have 3x squared, which is a constant. It doesn't contain 1, so it will remain as it is. So I can say it's gonna be 3 of an x squared, then I will open a bracket. Now I will differentiate AB with respect to 2y. I will start my differentiation first by differentiating f with respect to its own variables. The own variables are a and b instead of u and v. So I will do the same. Partial f partial a plus partial f partial b. But I need the differentiation with respect to y. So I will start once more differentiating the a with respect to y and the b with respect to y. So once more, it's gonna be partial a partial y, then partial b partial y, as you can see. That's the first derivative of the first term. Of course, I know that a is equal to z over x, I believe in here, and b is equal to y of, let me check this. Oh yeah, this is little over x, and the other one is y over x. I know now that partial a partial y is going to equal to 0, while partial b partial y will develop 1 over x. Now I know the derivatives. Then I will start substituting. So it's gonna be, if I need it, plus I have the substitutions. Okay, but now I will start differentiating this guy, which is gonna equal to a negative of an x times z. And in a similar manner, لاحظ Mr. Osman, now I will do the second derivative, but with respect to whom? To y. That's the first derivative. Let's start. So I will have x and z, which is out. I will differentiate this function with respect to y. In order to get the derivative of this function with respect to y, it means I will have partial 2f. I will differentiate the function with respect to its variables first. So it's going to be partial 2f, partial a squared, then partial 2f, partial a times partial b. That's the first step. I'm differentiating the first derivative with respect to the variables in f. Then I will drive my derivative to a and b. So I will multiply this guy partial a partial y, and same way like times partial b partial y. As you can see, I have taken this guy first. معايا في راس خدت الفانكشن اللي اسمها f, which is the function a and b. I will have to differentiate first with respect to its own variables, which is a and b. This is why we have partial 2f partial a squared, partial 2f partial a partial b. Then I will multiply by partial a partial y times partial b partial y. Now I differentiated the function with respect to its own variables. Okay, now I have the derivatives, so there will be no problem. Then I will go for the third term. This is the third term. If you remark the third term, I have two identities in y. The first part in y and the second part, which is also a function in y but embedded in the values of a and b. So I will have to differentiate the first times the second, then vice versa. So differentiating the first will develop negative of x times partial f partial b of an a and b. Then I will have minus xy. Then I will have partial f partial b, okay, the derivative with respect to y. In order to get the derivative with respect to y, I want you to remember once more, I I will have to differentiate the function first with respect to its own variables. So it's going to be partial. Second derivative, f, with respect to its own variables, partial, b, partial, a, then plus partial 2 over f, partial b in the 2 times. Then I will drive the derivatives with respect to y. So multiplying partial a, partial y, then partial b, partial y. This is how to drive the derivative of this function in all the terms. As you can see, it's not complicated, but it depends on organizing your answers very good, step by step. So now, let's see how it is written with you. So once more, that is the derivative with respect to y, that's the derivative with respect to y, and that's the derivative with respect to y. Remark each part of them. Now I will start differentiating for each one of them separately. Okay, for the first part, as I told you, I will differentiate first with respect to a, then b. For the second part, similarly like, here we go for the second part. Of course, substituting with the results of partial a, partial y, and the partial b, partial y in a similar manner in all of them. Now I will start substituting in all of them altogether. I will have the result as you can see. This is the final result. Once more, if I want to get the derivative for x squared, I will do exactly the same. Getting the derivative with respect to x, and then I will start differentiating with respect to x. So it's going to be 3x squared times f, then plus x cubed times partial f, partial x, or I can do it direct. So it's going to be 3x squared as I told you, then partial f, partial x. Here, x is f is a function in x and z, so I can differentiate it really very simple. Here is the result. Here is the derivative of partial f, partial x. It's also an arbitrary function. And if I want to do the second derivative, I will start once more to have sense of x times f. Then I will start separating each one of them. And that's the final result as you can see. Okay, this problem, it's really a very nice problem for us. And it already exists in the main slides. Of course, if you didn't attend the previous session, which we did go through the Jacobians, okay, of composite functions, this is not going to be an easy for you. But try just to follow up with me as much as possible in this part. Okay, it's really major to study the previous lectures. Here he is giving you f, a function which maps from R2 into R2. But I functions from the 2 dimension into imaging it, or the result will be in R2. Okay, how this function works? Simply for every x and y, it will change them into the first component 1 plus x and y, this is f1, and e to the power of x minus 1, this is f2. أنا عندي R2 into R2 يا فراس. This is R2 which is x and y. بص للاوتبوت اللي موجود برضه في كام كومبوننت؟ 2 كومبوننت. يبقى فعلا بياخد R2 بيودي مين؟ R2 بياخد x و يطلع 2 كومبوننتس. اوكي بيكمل وبيقول اتس نوت ذات جي دي فانكشن انت مش عارف هي عباره عن ايه برضه from R2 into R2. يبقى انا عندي الاف R2 وعندي جي R2 is a differentiable function. انا عارف انها كان بي differentiated. That g of 0y, خلي بالك من الجمله دي مهمه قوي. That g of 0y is equal to y and 0, which means if I have g at 0 and 2, the result will be 2 and 0. If I have g of 0 and x, the result will be x and 0. You read me? That's the function. And also he gave you partial g partial x is 0 negative 1, partial g partial y 0 negative 1. The value of the first derivative of g with respect to x at 0 negative 1 is equal to 1 and 1. And also in a similar manner, the derivative of g with respect to y at 0 negative 1, it's also 1 and 1. So you already have the results. He wants you to evaluate the Jacobian of f composite g, okay, at 0 and negative 1. So I need to get the Jacobians. According to the rules, or to the rule of the Jacobian that we talked previously for composite function, I have f of g of x, which is gonna be, I will get the Jacobian, okay, of f in g, then I will get the Jacobian of g, as you can see. So I will get the Jacobian first, that is a function in g. Then I will multiply it by the Jacobian in g, and they get the results. This is very, very simple. In order to get the Jacobian of f, I will need to differentiate this function. So the Jacobian in f, this is Jacobian in f, it will differentiate the first function with respect to x and y. So I will differentiate 1 plus xy with respect to x, which is going to be 1. I will differentiate 1 plus xy with respect to y, which is going to develop an x. Then I will take the second part, which is e to the power of x minus y, differentiating it with respect to x, which is going to be e to the power of x minus y. Then taking this guy, differentiating with respect to y, it's going to be e to the power of x minus y times negative 1. That's the Jacobian of f in general for x and y. But I'm not getting the Jacobian of f at x and y. لا أنا بجيب Jacobian of f at g. At first I will have to apply g. Then after applying g, I will start substituting in this function. Take care إنه g at 0 and y equal y and 0. He need me to find the Jacobian at the point 0 negative 1, which means the value of g and the 0 and the negative 1 at 0 and 0 and negative 1 will equal to, according to this fact, it's a negative 1 and 0. Those are the results that will be used in here. Standing before x equal to negative 1 and y equal to 0. Those are the values that I'm going to use here in substitution. Now I can get the value of the Jacobian of f at g at 0 and the negative 1. Those are the results. So I will start substituting. So it's gonna be, start substituting. I will replace y by its value, which is negative 1. I will replace x by its, the g of 0 and 1, as I told you, this is the output, which is negative 1 and 0. So I will replace y by 0 and the x by negative 1. Similar manner here, I will put y equal to 0 and the x by negative 1, so it's an e minus 1. In a similar manner, it's going to be negative e to the power of negative 1, as you can see. Remark, in the middle of what we are saying, I'm getting the value of the function g at 0 negative 1. The value of this function, is simply negative 1 and 0. So this is why instead of substituting by 0 and negative 1 as well, I have substituted by negative 1 and the 0. Because that's the meaning of the function. Now I had this guy. Okay, I will need to multiply it according to this rule. I will need to multiply it by the Jacobian of g at the point 0 and negative 1. And this is given for us. Differentiating g with respect to x with respect to y, and differentiating g with respect to y with respect to x will develop 1 and 1. So it's going to be 1 and 1 and 1 and 1. Now, I can get the Jacobian, okay? I can get the Jacobian matrix of f composite g at the point 0 and negative 1, which is going to be simply the multiplication of these two Jacobians times each other. I will multiply this Jacobian by the other Jacobian. Okay, let's do it once more, step by step, using the slides. So, once more, as I told you, in order to get the Jacobian of the composite function, I will get first the Jacobian of f composite g, that's the Jacobian of f composite g, times the Jacobian of g in x and y. The Jacobian of f times g, it means I will differentiate the first function once for x and the second for y. I will differentiate the second function with respect to x, then with respect to y. Differentiating will give you this result. Now I need to get the derivative of f at g, but not in any g. No, I need g at 0, -1. For g's of 0, the value of y, the result is y and 0. So now, to get the value of f at g of an x and y, I will have to use the result that g of 0 and the negative y of 0 and the negative 1 equal -1 and 0. So that's the result of the function that I'm going to use. Now substituting by -1 and 0 in these values. This is going to be 0, that's going to be -1. So that's the result of the Jacobian of g in specific at the point 0 and -1. Which is required. All I have to do is to find this guy. It is already given that the partial derivatives at 0 and -1 is equal to 1 and 1. So differentiating the g function with respect to x and y, differentiating g function of the part 2 with respect to x and y, it will give you the similar manner, the same results, which is 1 and 1. That's the Jacobian is going to be 1, 1, 1, 1. All I have to do is to substitute. I will replace the first Jacobian by this matrix and the second by that matrix. Here we go. Multiplying the two matrices in each other. Okay, multiplying will give you the result -1, -1, 0, and 0. This was the alternatives that was given at the beginning of the problem, so it's going to be the correct answer, the first one. This is really very close to what you are going to see on model on your exam. Because the first midterm that you will have, it's going to be on model, as you know. And it's going to be on the 10th of March. Are you with me, Mr. Fras? Okay, very good. Any questions? Please, you will have to review the first lecture. Very important to go through it. Because we had the Jacobians, we had the partial derivatives, we had the chain rule, and it's very, very important. Okay, in this part, I want to show you some of the problems from the workbook, and it's all related to this session. So I'm going to skip it for the time being, okay? Because it's also will depend on what we talked previously, but please try to remark what we are doing, okay? Consider three functions, okay? Consider the three functions. F, this function, take the positive side of the real numbers and map it into R. Consider also G, which maps from R into R. And consider H, that's a new function. H is a composite function, as you will see, such that F and G, both of them are differentiable. It is given all these values. He give you the value of function 3. S3 is equal to 2, the derivative at 3 is equal to 4, the value of G is at 2 is equal to 7, the derivative at 2 is equal to 5, and he gives you now the definition of of H. H is the composite function G composite F. Type, just in a quick question, G composite F, which means, as you know, as you know, that H is equal to G function as composite of F. So that's the definition of the composite function, as you know. Okay. Now I have F, I have have G and I have, as you can see, H. Remark for us, I can get here, for example, here, I can get G as a composite F, but I can't get F as a composite of G. Because G composite F, it can work. Because F of X maps R positive into R. يعني بياخد ال R positive, الجزء الموجب من real X, you represent it or you imply it or you give it an image in all the real numbers. خلي بالك ان الجي بياخد من R into R. معايا يا شباب؟ معايا فراس؟ يبقى ده بياخد من R positive into R في حين الفانكشن اللي جوه بتاخد من ريال لريال. لكن يعني معنى ذلك ان الكونديشن فور اف عشان يشتغل اوكي وركينج. لكن بص يا فراس، لو انا جبت اف كومبوزيت جي مش هيشتغل، لان الجي بياخد من ار يطلع ار. الاف مش بيعمل كده، الاف لازم ياخد مين بس؟ ار بوزيتيف، فمش هينفع الاوتبوت يدخل هنا. يبقى اذا الاونلي سولوشن فور مي از تو جيت جي كومبوزيت اف، وهو ده اللي هو عايزه تحسب اتش كومبوزيت. هو ده خلاص اداك الديفينيشن، صح؟ هو عايز اول حاجه بيقول لك define the domain and the differentiability domain of H. قول لي فين الدومين وفين الديفرنشابيلتي دومين بتاع مين؟ بتاع الاتش. طبعا الاتش جي كومبوزيت اف، يعني معناها ان الاتش الدومين بتاعها في الاساس لازم يكون الدومين بتاع مين؟ بتاع الاف، لانها عباره عن الجي بس مين اللي بيدخل فيها؟ اف، وينفع عشان تشتغل لازم الدومين بتاعها يحكم. طيب بعدين هات اتش داش ات 3 ومن هنا هحتاج المعلومات بتاعتي. بعدين justify that the value of the limit. طيب لو انا بدات باول حاجه، لو انا بدات باول ستيب، اول نقطه انا عارف ان الدومين اوف اتش اوف اكس هي جي كومبوزيت اف اوف اكس. since f of x from r positive into r, so the domain of f of x is 0 up to infinity او x is greater than 0. يبقى انا عرفت على طول الدومين which is r positive. So h of x is well defined for all values x is greater than 0. Meaning it is also differentiable. The domain is going to be, as I told you, from 0 up to infinity, and the differentiability will be exactly the same. Since f is differentiable, G is differentiable, then the composition of both of them will also be differentiable.